Nuclear fuel production begins with uranium mining. Next, uranium is enriched, which means that uranium-238 and uranium-235 atoms are fission, since thermal, slow, neutron reactors require uranium-235 nuclei. The enriched uranium is converted from gaseous to solid state, mixed with a plasticizer, and compressed to produce pellets. These pellets are further sintered at high temperatures. The pellets weigh just a few grams, but have a large energy potential equivalent to 400 kilograms of black coal, 250 kilograms of crude oil, or 360 cubic meters of natural gas. The pellets are placed in heat-producing elements, fuel rods, sealed tubes made of zirconium alloy. The fuel rods are assembled into individual cassettes. One cassette may contain several hundred fuel rods, and the nuclear reactor core may contain several hundred cassettes. After the cassettes have been loaded into the reactor, a controlled nuclear reaction is started, during which there occurs uranium nuclei fission with large amounts of heat released. The resulting heat is transferred to water through fuel rod claddings in several circuits. Under pressure, the heated water turns into steam, which rotates the steam turbine. The steam energy is first converted into mechanical work. Mechanical work is then converted into electric energy by means of a power generator. The operation of thermal, slow, neutron reactors results in formation of spent nuclear fuel, a cassette with partially burned fuel composition. In this composition, up to 90% refers to atoms of uranium-238, which is unsuitable for use as fuel for thermal, slow, neutron reactors. The spent fuel is withdrawn from the reactor and sent to spent fuel storage pools where it is stored for several years, after which it is removed from the nuclear power plant for disposal or requires special waste burial conditions. Thus, a typical process diagram for nuclear energy generation leads to formation of problematic and environmentally hazardous waste. Therefore, scientists began to wonder how to organize a closed cycle, which allows for nuclear fuel recycling. This task can be addressed by means of fast neutron reactors. The concept of such reactors involves using fast neutrons. When exposed to the latter, uranium-238 nuclei, which are a waste product of slow neutron reactors operation, fission with some energy released and form plutonium-239, which can also be used as fuel for thermal, slow, neutron reactors in admixture with uranium-235. Fast neutron reactors make it possible to close the nuclear energy generation cycle and to ensure nuclear fuel recycling. Spent fuel is processed and sent back to thermal, slow, neutron reactors. There is a large amount of previously buried nuclear reactor fuel containing uranium-238, and according to preliminary estimates, it will last out several hundred years. The technology for producing mixed uranium and plutonium fuel, or also known as mixed oxide fuel, MOX fuel, for slow neutron reactors includes 3 stages. Preparation of molding powder. Compression molding of pellets. Sintering of pellets. If pellets are made on the basis of several constituents, for example, uranium and plutonium dioxides, the powders should be pulverized and mixed. At this stage, the operability of nuclear fuel in the reactor is ensured to a great extent, which depends on mixture homogeneity, grain density, grain size, microstructure, etc. In the existing process lines for production of reactor uranium and plutonium fuel, the initial powders can be first mixed and then pulverized, or mixed and pulverized at the same time. Ball or hammer mills are used for this purpose. However, such mills prove to be low efficient in pulverizing and mixing the initial powders. Therefore, after the pellets have been sintered, a clear separation of 2 phases can be observed, which indicates the lack of required homogeneity. In addition, the actual process is time-consuming and takes from several to dozens of hours. Thus, Globecore has developed an alternative innovative technology for producing MOX fuel for nuclear reactors based on vortex layer devices. Vortex layer devices use a fundamentally different method of impact on substances compared to ball and hammer mills. The initial powders of titanium and plutonium dioxides together with ferromagnetic particles are fed into a titanium container, which is placed in the operating chamber of AVS device. After starting the device, the container performs an axial reciprocating motion. An inductor creates a rotating electromagnetic field which causes ferromagnetic particles to start moving along complex trajectories and to constantly collide with particles of processed powders, with the operating chamber walls, and with one another, generating a vortex layer. Meanwhile, the processed powders are exposed to a number of factors in the operating chamber as follows. Rotating electromagnetic field. Direct impacting of ferromagnetic particles. Acoustic and ultrasonic vibrations resulting from collision of ferromagnetic particles. Magnetostriction of ferromagnetic particles, etc. The comprehensive effect of the above listed factors ensures rapid dispersion and homogenization of initial powders, which means achieving the high-quality molding powder of MOX fuel for production of fuel rod pellets. Given the occupational hazard to operating personnel, automatic mode is used for feeding of initial constituents and ferromagnetic particles, as well as for cooling and discharge of finished molding powder. The vortex layer devices manufactured by GlobeCore have the following advantages when used in the MOX fuel production processes. They properly pulverize and mix the initial powdered constituents, ensuring that the powders are uniformly distributed throughout the pellet. They pulverize and mix, as well as activate the constituents. The expected result is higher fuel burnup. The pellets produced on the basis of powders processed in a vortex layer device completely dissolve in nitric acid, which is important for reactor fuel regeneration. Unlike ball and hammer mills, the constituents are processed in a matter of minutes rather than hours or dozens of hours. The device is compact by dimensions and easy to integrate into the existing process lines for reactor fuel production. The device can be used in various process diagrams related to production of nuclear fuel for fast and slow neutron reactors when finely dispersed powders and homogeneous mixtures are achieved. And what kind of MOX fuel production equipment do you use? Share your experience in the comments section. For more information about the GlobeCore nuclear fuel recycling technology, please follow the link in the first comment or visit our website, www.globecore.com.